Hello everybody, welcome to today's research presentation. I'm Sam Kadarab, and today we're diving into a fascinating paper from the 2025 ACM Conference on Computer and Communications Security. The paper is titled DiveFuzz, Enhancing CPU Fuzzing via Diverse Instruction Construction. This work comes from researchers at the Chinese Academy of Sciences, and it tackles a really important problem in hardware security. How do we find bugs in CPUs more effectively? So, what's the big idea here? CPUs are incredibly complicated pieces of hardware, and before they are manufactured, we need to verify that they work correctly, that they don't have any bugs, security vulnerabilities, any possible ways for bad actors to get into the hardware or for the end user to have a piece of hardware that doesn't operate as expected. One popular verification technique is called fuzzing, which you may know from software security. Here's the problem, however. Existing CPU fuzzers are very inefficient and shallow. And by inefficient shallow, they take very long to generate meaningful bugs results, and they don't touch on hard to find bugs that a human designer would be able to find manually, whether over the course of days or weeks. Fuzzers generate a lot of repetitive test cases by nature of fuzzing, and they don't explore the state space very thoroughly. Now, this matters significantly to fuzzing specifically because if you keep testing the same thing over and over again, you are wasting time and not finding bugs, which is the end goal of fuzzing and the CPU verification. DiveFuzz's goal is very simple, but the idea is to make CPU fuzzing more diverse and more balanced in what inputs are being given to the hardware design so that we can find the bugs quicker and hopefully find more deep bugs in the CPU. Before we go any further, let's take a step back and quickly ask, what is CPU fuzzing? Well, CPU fuzzing is very similar to software fuzzing, where you have a program and you're throwing random inputs at the program to see if it crashes. And you repeat this process typically with something like guidance, where you throw an input and you measure what parts of the software it has covered, and you repeat these tests to see which inputs get further coverage, covering more test cases within the program itself, and with whether any of these actually cause a crash in the program, and ideally you get 100% coverage and your program doesn't crash at all. CPU fuzzing is very similar, but instead of the program now, we are testing a CPU or the hardware itself. This typical approach is differential testing, where you have two separate models. You have a golden reference model. Typically it's a simulator, which we trust to be 100% correct. And you have the actual CPU model itself. And you'll feed the same inputs from the fuzzer, the random instructions, to both, and you compare the two outputs. If they don't match, you may have found a bug. And since we are taking the reference model to be correct, that's the intended execution of the CPU, likely a bug will be found in the actual hardware implementation of the CPU. Now, there's two high-level approaches to this. You have program-level comparison, where you run an entire program, and then you compare the last and final CPU state after running the whole program. And you compare this to your simulator and check whether these two are the same. This is beneficial because it's very fast. You don't have to look at each instruction one at a time, and you can just run the whole program at once and then check the output is this correct. But then again, it's very coarse, and you could miss a certain bug that happens somewhere in the middle of the program, but it doesn't appear towards when that final output goes through. That's where instruction level comparison comes in, where you compare the state of the CPU to the simulator after each instruction. This is significantly more precise, but it's also much, much slower than the program level comparison. Now, why is CPU fuzzing especially hard compared to program fuzzing, for example, software fuzzing? CPUs are stateful machines, and what this means is that every instruction changes the internal states of the CPU, such as registers, the memory file, the execution flags, what's currently in the flip-flops, things like this. If your fuzzer generates instructions that always produce the same state changes, you are not exploring any new territory inside the CPU. You're not generating any new coverage for the CPU, the hardware. A simple analogy that I have as written as food for thought is if you're testing a calculator app and you only ever test 2 plus 2, 2 divided by 2, 2 times 2, you'll never discover that your calculator crashes if you try dividing by 0, or if you put in a really, really big number or really, really negative number. You won't discover that those cause a crash. This same principle applies to CPUs. If your fuzzer keeps generating the same division instructions, for example, with the same operands, you are missing all of the interesting edge cases. So we want to somehow generate instructions that test the different instructions with different operands to make sure you get all of those hard-to-hit edge cases. Now, the two core problems that the DiveFuzz authors identified with today's CPU fuzzers are, firstly, the low write-back diversity. And what does this mean? Write-back refers to the result that gets written to a register or to memory after an instruction executes. So if I do 2 plus 2, the output of the calculator will be 4, and then this gets written to the register or to a memory. If this data repeats significantly, then you are not exploring new CPU states. And you can think of this as if I do 2 plus 2, I get an output of 4. If I do 2 times 2, I also get an output of 4. So despite the fact that I did 2 different instructions, albeit the operands are the same, I still get the same output. Same case could go for if I do 1 plus 3, now the operands are different, but my result is still going to be 4, and my instruction obviously will still add, but the output will also be 4, and it will not explore a new CPU state for the write-back. Existing fuzzers often choose the operands randomly without understanding how this affects that write-back value. The second issue that DiveFuzz identified was imbalanced opcode distribution. So opcode is the operation code, such as addition, subtraction, multiplication. Some of these instructions get tested hundreds, thousands of times, while other instructions don't get tested that frequently. So like branch instructions, for example, could get skipped over despite the fact it may cause a much higher chance of you hitting a crash state. And this happens due to lots of different factors: decoding optimizations, branching behavior, instruction fusion. And together all of these problems add up to that we're wasting time fuzzing on essentially useless inputs. And we're also missing a lot of bugs because we're wasting so much time. If you only have 24 hours to fuzz, and half of those are useless instructions, well, might as well just fuzz for 12 hours with a real functional fuzzer that actually got unique data into the CPU. So what is the key insights that the authors found? Well, diversity matters. So the more unique instruction results that we can provide to the CPU, that means more CPU states can be explored, and that means more bugs can be found. And not only does we have to have a unique breadth of instructions, we need to make sure that they are all tested fairly and balanced. We can't just test the very fast and easy ones to test, like addition or subtraction. We have to test all of the instructions fairly. So the novel approach that the authors take here is that instead of just building the test cases statically, such as picking random instructions, random operands, it builds them dynamically using runtime context to make smarter choices. And so this means that they execute the instruction and they can see what is the write back state of said instruction. They can start building a table up of these instructions and pick ideal operands for the next instruction. So this table shows, for example, if we have a list of all these instructions, you can see the variation. Like, for example, load immediate, add immediate, and those are extremely common opcodes. We want to hit those ones that are not hit very often, such as the shift instructions or the rotate instructions. Those aren't hit very frequently, so we want to hit those more than the very common ones to cause more states to be explored. So at a high level, DiveFuzz has 4 main components. Borrowing from the figure that was in the paper here, firstly is the dynamic operand construction. So it interacts with the ISA simulator in real time while building the new test cases. It looks at the current CPU state, so what is in the registers, what is in memory, and then it chooses operands that will produce new results, not repeats. So you have the history, and it communicates with the simulator. We've had these additions in the past. We've had this add immediate in the past. We don't want to use those anymore. We've already tested those cases. Secondly is the semantic aware instruction streams. So instead of just doing random instructions, we want to make sequences that make sense. If I do a branch instruction at the start of the program, and then it jumps to some random address, and I have a bunch of add instructions afterwards, that's sort of gibberish. That's not a real data dependency between the two. The operands in the addition are not correlated with the branch instruction. The branch instruction is just there. So keeping track of these recently used registers and creating data dependencies between the instructions allow us to actually traverse the states in the CPU and to hit more coverage and deeper states in the CPU. Thirdly is the opcode balancing mutator. So this is similar to the diverse instruction construction, but now we want to actually balance out the opcodes. So if addition is getting all of the attention, it'll start putting less addition instructions into the mutator and might test more multiply instructions or more shift left instructions, for example. And then lastly, we want to eliminate false positives. So they have a false positive eliminator, which is differences between the CPU and the simulator that aren't actually bugs, but rather implementation differences. And so DiveFuzz will learn these patterns and avoids flagging these as crashes in the future, so you don't waste any time having to go through them at a later point. Now let's look at some results. This chart from the paper shows the write-back repetition rate, how often instructions produce the same results. So on the left here we have the DiveFuzz RTL and Cascade, 2 other state-of-the-art CPU fuzzers. And we can see the comparison between the two. For example, we have the write-back data repetition rates, and then we have the average repetition rates, and then we have the diversity of write-back data. And the relative repetition rate is around 90% for both DiveFuzz RTL and for Cascade, which is really, really high. This means that 9 out of 10 instructions that they are testing are producing results that they've probably already seen before. Now on the other case, we have DiveFuzz in orange in both of the diagrams. The repetition rate is only around 55%. Now that's still a lot of repetition, but the instructions that are produced are significantly more unique than what other state-of-the-art fuzzers produce, and this causes a huge improvement in coverage and bug finding ability. Now, numerically, you could think of this as well as DiveFuzz is exploring almost 2 times as many unique CPU states with the same amount of testing. Now, since we're testing, obviously, 2 times the amount of instructions, unique instructions in the same amount of time, we get to the performance numbers here. And this is where it gets very impressive. DiveFuzz, according to the authors of the paper, reaches 204 times faster than DiveFuzz RTL and 114 times faster than Cascade for the same amount of coverage. And then it's not just 2x or 10x faster. This is like 2 orders of magnitude, almost. And this is across the 5 different coverage metrics that are mostly considered the important ones. So control registers, multiplexers, code lines, ready valid signals, and signal toggles. And we can see that across all of the different metrics that the speed up is pretty significant, well within 100x or greater. But speed isn't everything. Even if we have a really fast fuzzer and it doesn't discover any new bugs, that's not going to be very helpful. So the authors also managed to find 26 new bugs, proving that not only is it faster, but their unique instruction finding algorithm can find new bugs. So they found 26 new bugs across 4 CPUs. There's a big list on the right here. So Jiangshan, CBA6, Rocket Core, and Nutshell. And then 15 of these were serious enough to get CVE identifiers, which is a way of marking vulnerabilities in the cybersecurity space. And so the bugs fall into several categories. We have calculation bugs, access control bugs, exception handling bugs, configuration bugs. And so each of those, so calculation bugs is the math is done inherently incorrectly. So 2 plus 2 could equal 5, for example. Access control bugs is the user is able to jump into kernel space when they're not permitted, or they're like jumping out of memory bounds. Exception handling bugs, think of what if you seg faulted and it wasn't caught, you would overwrite some core boot information and your system just goes down immediately. Or configuration bugs, where the settings of the system just get messed up from user space code that's running. So one bug that has a security impact, as listed on the previous slide, bug B5 on the Jiangshan CPU involves the management of a interrupt enable bits. So due to a flaw in how the status bits interact, an attacker could potentially manipulate interrupt handling to escalate their privileges on the CPU. So they could run some snippet of code that bumps them up to kernel level code, and they could run malicious code on someone else's system if they were running their user code space. And these CPU bugs aren't just about crashes or incorrect calculations. They could be security vulnerabilities that break isolation, leak data, or give attackers unauthorized access to the system. And 2 really big CPU bugs that were on Intel processors back in the day were Meltdown and Spectre, which exploited the look-ahead features and memory walling off features of those processors, giving unauthorized access to them. So those are an example of actually a real-life CPU bug that Intel had a patched in later processors. So why does this paper even matter, really? Well, firstly, it's the first work, according to the authors, to systematically address write-back diversity and opcode balance in CPU fuzzing. Previous fuzzers focused on other aspects but missed this opportunity to improve the 2 balancing and diversity features in CPU fuzzing. Secondly, it's open source, so the code is available on GitHub. Researchers and engineers can use it, build upon it, and potentially migrate this to other platforms other than RISC-V, like ARM or x86 maybe, and hopefully find other bugs that were missed in hardware. And sort of already leaned into this third point, but it has a real-world impact. The bugs were actually found in the CPUs that people use, so RISC-V is a very popular CPU platform, and finding these bugs is very important for the designers of the systems and also users of those systems. And so there's a broader idea here that diversity and balance matter in the testing, and it's not just enough to generate random inputs, but you also need to guide the randomness towards the unexplored parts of the CPU to hit those new states. Now, the big limitations of this paper are firstly the overhead of this dynamic construction. So the dynamic construction does take a significant bit of overhead to the fuzzing process, but the ISA simulator runs much quicker than the actual CPU simulation. So for larger designs, this probably isn't a large issue, mainly because the actual CPU simulation is the bottleneck. However, it does have the overhead of the dynamic construction. Secondly, the DiveFuzz as it is currently only works with RISC-V processors, so the concepts can apply to other instruction sets potentially, but the actual implementation currently is only RISC-V. And then lastly, you do need some manual effort because of the false positives. Despite the fact they have the false positive eliminator, there's still some that need manual review. And we can see in that little table on the bottom right there, there's around 84% on junction, and nutshell has a 95.6% elimination rate. So you'll have roughly around 15 to 5% false positive that the designer actually needs to go through. And it is a significant amount for junction. 1,700 or so bugs to go through is quite a large amount for a designer. So that's a very big drawback, but it is better than other implementations at the moment. Lastly, some ideas going through this paper were, would this approach be able to be extended to other hardware domains? So apart from CPUs, can other hardware ASIC designs benefit from diversity guided fuzzing, where you're looking at the output and trying to guide the fuzzing from the output instead of the input? Otherwise, can this be also applied to other fuzzings, sort of standard cell, the ASICs like I just mentioned, other architectures other than RISC-V? And then lastly, are there better algorithms for operand selection? Is the way they're selecting diversity and reducing repetition in DiveFuzz, is that the optimal way, or is there some other way that is better than what was explored here? If you're interested in learning more, this paper is available on the ACM Digital Library. I have the link here. The code is on GitHub. You can just search up DiveFuzz. It's on the N2Sec GitHub repository. It has all the code there. And yeah, this concludes this. I thank you for your attention. Hope I gave a good understanding of what DiveFuzz is, and hopefully I've intrigued you enough to go to the paper to dive deeper and read more about the details. Thank you again.